Hello guys, greetings to every one of you. Welcome to today's class. We will be looking at electric fields. So get ready for a wonderful lesson like today's lesson. We will be looking at electric field, like I said, and we are going to be looking at a lot of important, interesting things in physics today. All right, guys. The first thing first, we're going to I want to talk on the concept of the electric field. All right. So first thing first, the electric field is a region. Is a region in which a charged body experiences a force. A region in which a charged body experiences a force. Which force is experienced here? It is the electric force or electrostatic force. Now, as a characteristic of the electric field, it has what we call the electric field strength, represented as E. The electric field strength, the first thing you must know, electric field strength is equal to F, the force, divided by Q, the charge. What does it mean? It means that the electric field, electrostatic force experienced by a particle whose charge is Q is simply equal to Q times E. Okay, so far so good. Now, since we are saying that the electric field strength E is given by the force divided by the charge Q, now it means that the unit of the electric field strength is Newton per Coulomb. Now, what definition can we give to the electric field strength E? Electric field strength E is the force per unit positive charge on a stationary point charge. So it comes from the definition E is equal to force per unit positive charge. Now the next thing we'll look at is field lines. What are field lines? What are the characteristics of field lines? Without wasting of time, I would like you to know that we can represent the shape of an electric field by drawing forces with the use of lines. In an electric field, the line represents the direction of the force on a small positive test charge. Okay. Now let us look at examples. Okay, look at your screen. Watch your screen. You see 1, 2, 3. These are examples of electric field lines. So here you can see the direction of electric field lines. Okay, let's start with diagram A. Then we go to B and C. Take a close look at the three structures. Look at it closely, and then you're going to notice one thing, that the direction of the electric field lines, the direction is away from positive charge, and then it is toward the negative charge. If you look here, you see the direction, it is leaving the positive to the negative. Here, this is a positive charge, so the direction it is leaving, it is going outward, 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 outward. All right. So here, this positive, this negative, it leaves positive and goes to negative. For the negative, it is entering, and for the positive, it is going out. So what does it mean? It is centrifugal for the negative, centripetal for the positive. All right, that's it and done. Then the next thing you notice is that the closer the field lines, the stronger the field strength. where the field lines are closer. If you look where, you notice that, for example, here in diagram C, look clearly here, you see the lines are closer. When they are coming like this, they are closer. As they are going, they are getting far apart. The closer the lines are, the stronger the field strength. Okay, so good. That's so good. Now, another thing is, the third, you need to know that if you look at this and this, you are going to notice that the field lines, they never cross. Field lines, they don't come and cross each other. It is not possible. All right, so that's so good of you to have understood what I've said. Now, the next thing we're going to look at is the uniform electric fields. What do we mean by uniform electric fields? Now, coming back to this figure here, these lines that you can see here, the diagrams we are just from studying. If you look at A, you can see that once we get away from the edge of the plates, the field between two parallel plates becomes uniform. If you look clearly in A, you are going to see that this is what we're talking about. This is a uniform field. You see that this is it. Here now it is something different. Give me a minute. Let's see what's here. Alright, it's okay. Alright, so this is what we call a uniform fields. So once we get away from the edges of the plates, the fields become uniform. Look in in C, this is it here. This is what we're talking about. Here you also have a uniform field. Okay, so when you have a uniform field, what happens to the field lines? The field lines are parallel. Where you have parallel field lines, it means that what we have there is a uniform field. This means that wherever a charged particle is placed between those plates, it experiences the same magnitude of force in the same direction. All right, now we have to look at how to calculate forces on charges. All right, the electric field strength between the plates is given by the formula E equal to V on D. Now, when we say V, we are referring to the potential difference. V stands for the potential difference, and then now D will stands for the distance, separation, distance between the plates. So now, remember at first we said that E is equal to force over charge. Now we are saying that that same E is equal to V on D. Now, in the first scenario, we said it has unit Newton per Coulomb. So now, we are still going to say it can also have the unit of volt per meter. Very good. That's good. You have understood. That's very good. Let me read this out for you. Typical mistake. It is often thought that the force on a positive charge particle between two parallel charge plates is stronger than nearer one of the plates than when is stronger when nearer one of the plates than when midway between the plates. This is incorrect. Indeed, it contradicts the idea of uniform field. The field on the force on the charged particle is the same wherever it is between the two plates. The force on a charged particle is the same wherever it is between the two plates. All right. Okay, good. We look at an example on that. A piece of dust carries a charge of negative 4.8 times 10 to the negative 18 coulombs and lies at rest between two parallel plates separated by a distance of 1.5 centimeter. Calculate the force on the charge when the potential difference of 4,500 volt is applied across the plates. So now what do we have? We want to calculate the force in this situation. Right. We want to calculate the force, and then we are being given the charge. We are being given the charge in coulomb. We are being given again the potential difference. All right, so that's good. Now you know that F is equal to first of all E. Yes, you have that E is equal to V on D. Good. Yes. And then you also know that that same E is the same as F on Q. So what does it mean? It means that if you take this one, we are saying that F is equal to EQ. E times Q. Alright. So we have the charge. It is given. We have the charge. This is the charge that's given. Then Q, which is the charge. Sorry. The charge is given already. The charge is given, and then now V, which is the potential difference, is also given. Distance is given. All right. So it means you are going to use all these two equations. You use this one to have E, and then you use that E now in the second equation to finalize your answer. That is very good. All right, guys. Now let's talk on the effect of electric fields on motion of charged particles. All right. So good. A charged particle in an electric field experiences a force and therefore tends to accelerate. All right, so here you can see, for example, as we go through it, you see what is happening in a cathode ray tube. If the particle is stationary or if the field is parallel to the motion of the particle, the magnitude of the velocity will change. I will go through it again for you. I'll read that for you. It says a charged particle in an electric field experiences a force and therefore tends to accelerate if the particle is stationary or if the field is parallel to the motion of the particle. The magnitude of the velocity will change. An example is when electrons are accelerated from the cathode towards the anode in a cathode ray tube. Now, this is the diagram below here. Now, when you come down here, I said you should add the following must-learn equations. This equation and this equation. As we are going down, make sure you still remember it because it is of cardinal importance for you. All right, when we're done here, I want you to know that if the field is at right angles to the velocity of the charged particle, the direction of motion of the particle will be changed. The path described by the charged particle will be parabolic. Look, that means it will be like a parabola. You can see that in figure 10.3. You look here, you see. Good. This it takes the shape. the shape of a parabola, the same shape as a projectile in uniform gravitational field. All right. Now, the constant force on the charged particle leads to it describing a parabolic path. The path is similar to that of a ball thrown horizontally in a uniform gravitational field. Ladies and gentlemen, I will leave you at this level with some exercises, questions. Now test yourself. I will give you some time to watch your screen, copy the questions, and then, of course, answer them and submit either in the comment section or you submit in the designated forum. So here we have come to the end of our lesson on electric fields. Thank you for turning to us, and you have a wonderful time. See you again in our next lesson, and bye.